Chapter 3, Displaying and Describing Categorical Data. From these notes, we should be able to summarize data using a relative frequency chart, display categorical data using bar charts, segmented bar charts, and pie charts. So of course know the difference between those three as well, and describe data presented in the charts in order to make comparisons. The first rule of data analysis is to make a picture. The second rule of data analysis, make a picture. The third rule of data analysis then is obviously make a picture. The whole point is we need to be able to visually see what's going on with the data distribution so we can better analyze it. On that note, a distribution displays the possible values of a variable and how often it takes them. Depending on the type of data and what you are looking for, there are a number of ways to organize and display the distribution. When a variable is categorical, and remember categorical means that we're counting up the people or things or items in a specific category, the first step is usually to construct a frequency table, which displays the possible categories and the number of observations in each category. In this case, I've gone ahead and done a frequency table for my AP scores from last year. This part right here is the frequency table. If you add the rest, it's a relative frequency table. If you notice, I've left out the total. These add up to 42 students. And this tally chart is just useful when you're collecting the data. It doesn't need to be there. Okay, and then over here we have the relative frequency, which comes with this distribution, or definition, excuse me. The relative frequency for a particular category is the fraction or proportion of the distribution that the category appears in the data set. So in this case, 9 out of 42 students had a 5, which is about 0.214, which is about 21.4% earned a 5. And you would do that for all of them. What you may notice is if you did that for all of them, they would add up to 1 or 100%. That should always happen unless there's a rounding error. There are several ways to then display this data. Many of these you have seen before, so we're going to go over them very quickly. The first is bar charts and relative frequency charts. The area principle says that the area occupied by a part of a graph should correspond to the magnitude of the value it represents. For example, when making a bar chart, the rectangle should all be the same width, so only the height determines the area. Obviously, these are bar charts, whether they're horizontal or vertical. And the key thing is that the widths here are the same. I didn't make one skinnier, which could misrepresent the data. Also, I talked about a bar chart and a relative frequency chart. Really, the only difference is here's a bar chart we were counting up that I had 9 kids that got a 5, versus here, this is 21.4%. It's the exact same picture. We just have counts versus percents. Here are some hints. The horizontal axis should include the variable name and the possible categories. The bars should have some space between them to indicate they are freestanding and can be arranged in any order. I.e., do not make these touch. That is something else. Okay, that is a histogram, and we'll talk about that later. The vertical axis can be frequency or relative frequency and should include a numeric scale starting at 0. We'll talk about why that's the case. Also, relative frequency bar charts, which would be this one right here with the percents, can make it really easy to compare multiple distributions, especially when the sample sizes are different. So if I wanted to compare one class of 42 students and one class of 200 students, turning into a percents make it a better comparison. Right here, we have an ad from DirecTV, and we're wondering what's wrong with it based off the rules we just learned. Well, obviously, for number 1, the widths of each one are not even, which makes it look like DirecTV is a lot bigger, even though 95 is not that much bigger than 81. Also, there's no scale to help you tell that this is 95, and there are no labels. So there's some problems with this as a bar chart to begin with. Now let's look at pie charts or segmented bar charts. These are useful when comparing categories that form parts of a whole. Categories must not overlap, which means each subject must be in only one category. The DirecTV ad shouldn't be converted into a pie chart since some of the channels are more than one package. You could have HBO here and here, so we couldn't put it into a pie chart or a bar chart. segmented bar chart. We do have it in a bar chart here, which is poorly done, but we could not put it then into a pie chart or a segmented bar chart, which I also call a candy bar chart. So we have the food charts here. All right, so what if we wanted to compare the distribution of my AP scores to the global AP scores? Well, we can use multiple pie charts, comparative bar charts, or segmented bar charts. Note, my scores in the table down here are different than the ones above because I had to take out the kids that did late testing to do the global comparison. So my kids actually did better than what's in this table. So here anyway is my frequency chart. And you can see that if you exclude my kids that took late tests, 13.3% of my kids got a 5, 13.9% globally got a 5. 40% of my kids got a 4, while only 21.7% of global students got a 4, etc. So we could present that in a pie chart, and it's okay to do this because there's no overlapping. You can't get a 4 and a 5. Notice that they are labeled and that the spaces are representative. This really is about 25% of the circle. You could also do that in a segmented bar chart, which is the same thing but in a candy bar shape. And I put it on a scale so it's easy to read. And then I've labeled everything. Okay, a graph or a chart without labels is absolutely useless. Lastly, we have the comparative bar chart, which is the same as we did before, but we put both categories next to each other so you can really compare. I think you've seen these before, so I'm going to have you go ahead and write a comparison statement of my scores based on the global scores. Make sure you talk about both distributions. So Cleicas' scores were this compared to global, and write a couple of sentences. Now let's look at the next page. When we look at two categorical variables at the same time, we often arrange the counts into a two-way table, also called a contingency table. For example, a recent article in the Journal of the American Medical Association, and it's not that recent since it's 2002, reports the results of a study designed to see if the herb, St. John's wort, is effective in treating moderately severe cases of depression. The study involved 338 subjects who were being treated for major depression. The subjects were randomly assigned to receive one of the three treatments, St. John's wort, Zoloft, or a placebo, for an 8-week period. Please describe the W's and an H. We will check this in class. But let's talk about this table. The margins of the table, bottom and right, are called marginal distributions of the two variables. The cells in the table, so the cells in the middle, count the frequency of each combination of two variables. So if we said how many people took the placebo and had no response to placebo, that would be 66. It is also possible to use relative frequencies, but there are several ways this can be done. 66 out of 338, so taking a number from the inside over the total, is the proportion of people who took placebo and had no response. That's a total percent. 66 out of 116, using the denominator from one of the margins, is a column percent, and vice versa, you could get a row percent. I think all of you have done this in your secondary classes. Finally, did the response of the subjects depend on which medication was given? To determine this, we can compare the conditional distribution from each medication. A conditional distribution looks at the distribution of one variable when the value of the other variable is fixed. For example, here are the conditional probabilities for St. John's wort. I'm going to go ahead and clear my table. And we're just going to look at St. John's wort. So we only care about the 113 people who took St. John's wort. So that's why our denominator is 113. How many of them had a full response? 27. So this is my conditional probability. All three of them together, which would add up to 100%, that would be my conditional distribution. And I'm going to have you go ahead and calculate the conditional distributions for Zoloft and placebo. Make sure you pause the video, show work. So I want fractions and decimals. Lastly, I want you to fill in the missing parts of the charts below for the placebo data. So go ahead and make a comparison right here and also right here based off the examples from the previous page. And do the results look the same for all three medications? We'll discuss that in class. Write an answer. Finally, if the distribution of one variable, the response, is the same for all categories of the other variable, which would be the medication, we say the variables are independent or they have no association. If two variables are independent, then knowing the value of one variable will not help you predict the value of the other variable. For example, if knowing what medication a person received doesn't help you predict their response, then the variables are independent. So if 50% of all the subjects felt better, whether they took the placebo or Zoloft, then we'd say they were independent. Or even if 70% of all the subjects felt better, but they had the same percent, then there was no association between the drug and feeling better, so it was independent. If the distributions are not the same for each category, we say the variables are dependent or that they have an association. For example, if knowing what medication a person received helps you predict their response, then the variables have an association. Lastly, let's discuss the Simpson's paradox. Sometimes it is inappropriate to average proportions. For example, suppose you are a baseball manager and need to choose a hitter for a certain situation. Player A has 33 hits out of 103 at-bats, while player B has 45 hits out of 151 at-bats, which makes it seem like player A did a lot better. He's got 32% versus 29.8%. However, against right-handed pitchers, player A has 28 hits and 81 at-bats, or 34%, and player B has 37%. Also against left-handed players, player A has, so basically let's look at this. Okay, if we look carefully, I'm not going to state all the data. This person overall did better. He has 32%. However, his versus right-handed is lower than player B, and his versus left-handed is lower than player B. So he did worse versus right and left-hand players, but when you average the two, his overall seemed better. That is Simpson's paradox. How can this be? It seems like hitting against left-handed pitchers is more difficult, and even though player B is better in both cases, since player B has more at-bats against left-handed pitchers, his overall average is low. Fortunately, Simpson's paradox is fairly rare. Another example of Simpson's paradox can be found on page 35. Before you come to class, write some questions down, maybe what you still need help with or what struck you. We'll talk about it in class, and then also go ahead and fill in the summary sheet that I gave you. Thank you.